So plugging along with our reaction mechanisms, the next couple of reaction mechanisms are going to look at hydrolysis reactions. Reaction mechanism 18 here is going to look at the hydrolysis of peptide bonds that we find with amides, and then reaction mechanism 19 is going to look at the hydrolysis of ester bonds that we see with triglycerides. We'll talk a little bit more about this later, but this reaction mechanism highlights chemistry that we're going to see when we look at serine proteases, which are important digestive enzymes that facilitate the breakdown of protein in your digestive tract. Why all of these reaction mechanisms are important is as we begin to understand enzyme catalysis, we first look at the uncatalyzed reactions so that we understand how amino acid chemistry happens, and then we think about how we might need some necessary cofactors when amino acid residues aren't able to help out. So I recently switched the order of reaction mechanisms, so I have to change the text a little bit here. This reaction mechanism begins, as we are actually going to see in our next reaction mechanism for the hydrolysis of esters, but we're going to protonate the carbonyl to allow it to be a better electrophile. A lot of times when we're doing hydrolysis reactions, water not being a strong base is not going to be as strong or good of a nucleophile. So we facilitate chemistry by making the carbonyl a better electrophile by protonating it. Keep in mind that we need to think about having a situation where we don't have an improper protonation sort of state. So in this case, our nucleophile is not so basic that we risk protonating it as well. Water's not so basic that we're all of a sudden going to generate hydronium ions. But again, that's in contrast to what we saw with reaction mechanism 16, where we had amines that were our nucleophiles. So going ahead here with our mechanism, we're going to begin here with our amide. And we highlighted that we wanted to protonate this amide in order to facilitate it being a better electrophile. So in most cases here, remember we want to have solvents serving as the proton donor or proton acceptor. So now that we have this protonated amide, it's much more susceptible to nucleophilic attack by water. One of the things that we're going to highlight here after we finish this mechanism is sort of the importance of different steps in our reaction mechanism and making sure that we don't happen to have a step happen sooner than it's supposed to and create a protonation state that's not reasonable. So that's going to be something we'll talk about for this step right here. So again, we can deprotonate what was our incoming water nucleophile, and then we can protonate here our amide, since we want this to be our leaving group. So having a neutral or relatively neutral intermediate here is going to be important. So now we can have decomposition, essentially regenerating a carbonyl here, departure of our protonated amine, which is now a good leaving group. Generates this carboxylic acid here. So used to writing protonated amines, but this comes off as an unprotonated amine. And I'm actually going to show this as an intermolecular reaction here, since these species are likely to be close to one another, not unreasonable to think that they might kind of facilitate chemistry. I'm going to return to this and kind of highlight the fact that we are seeing a one-way arrow here. So we'll come back at the end and sort of talk about that. But again, we're going to end up here with a carboxylic acid. and now a protonated amine. And it's likely, based on physiological pH, that we are going to have this carboxylic acid in its deprotonated state. And by having a deprotonated carboxylic acid, that's a very poor electrophile because it's actually fairly electron rich. And by protonating amine, this is no longer a nucleophile. And both of those reasons account for the fact that we have a one-way arrow there. We make that last step irreversible. So that's kind of the correct mechanism. What I'm going to do on the next slide is I'm going to highlight kind of some things to think about with what's going on in this sort of intermediate here. And clearly there's a deprotonation step that's going to happen of this oxygen here, but we need to make sure that it doesn't happen too soon. So again, note of warning, I'm going to kind of highlight here, this is not something that is going to be a correct mechanism to highlight something that we want to make sure we don't do. So let's start with our amide here. So even though it's not necessarily incorrect to think about water acting as a nucleophile and doing some chemistry here, generating this alkoxy intermediate here, if we continued with this mechanism the way we saw on the previous page, we would say, well, we don't want our incoming nucleophile to be a good leaving group, so we need to deprotonate it. And we want our amine group here to be a good leaving group, and so we're going to need to protonate it. So while that logic is sound, if we look at the intermediate that we get here, it's not really logical from a protonation state. So really, again, and just finishing out this mechanism here, right, if we were to take and then say, let's decompose this, have this guy depart, and we get our carboxylic acid and our amine, as much as it's tempting to do that because it seems like our mechanism is simpler, the problem inherently is with this guy right here. And again, if we think about pKa values here, pKa value for an alcohol would be around 15 to 16. So we're not likely to have an alkoxy group in this deprotonated state and not also have our amine be deprotonated. Remember, the pKa of protonated amines is around 9 to 10. So if this guy is going to be protonated, we are certainly in an acidic enough environment that this guy would also be protonated. So again, if we compare this to the correct mechanism that we just did on the previous slide, again, you can avoid this complication by making sure that we don't deprotonate the alcohol until after the amine group has departed. So we can see that we do deprotonate this guy, but not until after we have departure of this guy. Now again, it wouldn't be incorrect to kind of start from this guy and show deprotonation at this time. Use these electrons to come down and then have that departure. So it's possible that you could think about combining these two steps as a way to kind of facilitate your mechanism. That would be okay. But we just want to make sure we don't have something that's existing that's not likely to be feasible based on pKa and protonation state.